Hello everyone, my name is Fatina Nadira and welcome to our presentation Heuristics and Computational Thinking in Mathematics for Educational Change.
And I am Adam, your AI co-presenter. I will be joining you today to explore how heuristic strategies help us solve problems efficiently, especially when perfect solutions are not practical.
Today, we aim to explore how heuristics are used in math, demonstrate problem solving using computational thinking, solve three problems which is easy, intermediate, and advanced, and finally show how these strategies help change education. Heuristics are like mental shortcuts. They are not guaranteed to be perfect, but they are useful when solving problems quickly, especially under pressure or uncertainty.
Right. For example, I use heuristics when navigating data or choosing between multiple actions. It is about finding a good enough solution first.
Computational thinking, on the other hand, is a structured approach to solving problems. It includes four main elements, which is decomposition by breaking down problems, pattern recognition by identifying similarities, abstraction by focusing on what matters, and algorithm design by using step-by-step instruction. Our essential question is how do heuristics and computational thinking drive educational change?
The answer lies in how they promote critical thinking, problem solving, and digital readiness, all vital for both students and educators.
They empower students to solve problems independently, creatively, and prepare them for jobs that may not even exist yet. We will now walk through three problems, which is an easy logic puzzle with fruit box, a number pattern problem with multiples, and a network design problem using graph theory. Let's start with simple problems. We have three box labeled incorrectly. One says apples, one says orange, and one says maize. You can only pick one fruit from one box. How can you fix the labels?
Sounds tricky, but here is a clue. All the labels are wrong. That means the box label means cannot be means.
First, we need to pick a fruit from the mixed box. Say it is an apple. That box must be apples only. The one labeled oranges must then be mixed, and the remaining box is oranges.
That is smart deduction. Using decomposition to focus on one box, pattern recognition to spot the logic, and algorithmic thinking to relabel systematically.
This is also a common strategy AI use, testing one variable to determine the others. Next, let's find the sum of all numbers below 1000 that are divisible by 3 or 5.
That is 3, 5, 6, 9, and 10, and so on. Sounds like a lot to add.
That's where algorithms come in handy. To solve this, we need to find the sum of all numbers below 1000 that are divisible by 3 or 5. Instead of listing and adding them one by one, we can use a shortcut by using a formula from arithmetic sequence. First, let's calculate the sum of all multiple of 3 below 1000. The smallest multiple is 3 and the largest is 999. To find how many terms there are, we divide 999 by 3, which gives us 333 terms. The formula for the sum of arithmetic series is sum equals to first term plus last term multiplied by number of terms divided by 2. So for multiples of 3 is the sum is 3 divided by 999 multiple 333 and divide by 2. Next, we do the same for multiples of 5. The first multiple is 5 and the last is 995. Dividing 995 by 5 gives us 199 terms. The sum is 5 plus 995 multiples by 199 and divide by 2. Now, here's the important part. Some numbers like 15, 30 and so on are counted twice because they are divisible by both 3 and 5. These are the multiples of 15. We need to subtract them once so we don't double count. The smallest multiple of 15 is 50 and the largest below 1000 is 990. Dividing 990 by 15 gives 66 terms. The sum is 15 plus 990 multiplied by 66 and divide by 2. Now we add the sum of multiples of 3 and 5, then subtract the sum of the multiples of 15. Total is equals to sum of 3 plus sum of 5 minus sum of 15. This gives us the correct final answer efficiently without needing to manually add hundreds of numbers.
That is pattern recognition, algorithm design, and abstraction, which is a key computational thinking steps. I use this when optimizing data search or filtering information.
Our final problem is designing a computer network with the lowest connection cost. Here are the connection costs between computers A to E.
That's a classic minimum spanning tree problem, which is one I often solve in routing algorithms and logistics.
Our final problems involves designing a computer network using the lowest total connection cost. We are given 5 computers, which is A, B, C, D and E, and the cost of connecting each pair. The goal is to connect all the computers using the minimum spanning tree method, where we connect all the nodes with the lowest total cost without forming any loops.
Sounds like something I do when optimizing data networks. Which method are we using? Are we using Pascal's or Prism's method?
For simplicity, let's use Kruskal's algorithm. We will start by listing all the connections in order of increasing cost. First, B to C cost equals to 1, A to B cost equals to 2, A to C cost equals to 3, B to D cost equals to 4, C to D cost equals to 5, D to E cost equals to 6, C to E cost equals to 7. Now, we select the smallest edges step by step, making sure we don't form any cycles.
Alright, I'm following. Let's put the minimum spanning tree.
Step 1. Start with the smallest connection, which is B to C with a cost of 1. Step 2. Next, we connect A to B, which is cost 2. So far, we have A, B, and C connected. Step 3. Add B to D with a cost of 4. Now, we have 4 computers connected, which is A, B, C, and D. Finally, we connect D to E with a cost of 6. That connects all 5 computers with no cycles.
Let's add this up. 1 plus 2 plus 4 plus 6 equals to 13. That is the minimum total cost to connect the network.
Exactly. We skip over higher cost options like C to D, which is 5, C to E, cost 7, because including them would have created cycles or increased the total cost.
This is a perfect example of decomposition, which is breaking the network into small parts, pattern recognition by finding the cheapest connections, and algorithm design by using Kraskell's method to build the optimal solution. It is also the same kind of logic I use in network routing and AI pathfinding.
So, the final answer is that the minimum cost to connect all 5 computers is 30. And we use a clear step-by-step heuristic to get there. To conclude, heuristics and computational thinking simplify complex problems. They train us to think logically, step by step.
And when students use these skills, they are preparing to collaborate with technologies like me. It is a partnership that makes problem solving even more powerful.
And that brings us to the end of our presentation. We have seen how heuristics and computational thinking can be applied to different levels of mathematical problems, from simple logic puzzles to more complex optimization challenges. Thank you so much for your attention.
And we have also shown how these same problem solving strategies and real world problem solving
Thank you so much for your attention. We hope this presentation has inspired you to think more critically, solve problems creatively, and see how human thinking can work hand in hand.
Until next time, stay curious and keep thinking computationally.
Thank you.